Hi everybody, welcome to K-pop guide for General Physics 1 called the Series X. I'm Jung-il Lee, the director of the K-pop Collaboration, Korea Pragmatist Organization for Physics Education. K-pop was established in summer 2019 when I served as the chair of the physics department in Korea University. We have renewed all of the 18 general physics experiment program in Korea University with a set of brand new programs and have replaced old-fashioned homework system of general physics course with the YouTube interactive evaluation system. Most of the experimental devices were actually invented by K-pop collaboration without support from government or school. Now our efforts are focused on replacing general physics textbooks such as Halliday and Resnick that has been used for more than 40 years with a brand new style online textbook and lecture series that can always be accessed for 24 hours, 365 days. I hope these free online version textbook and lecture series in various levels of physics could help anyone who wishes to study physics. So I hope you could enjoy this program and subscribe to K-pop channel. The K-pop members will be very happy if you could subscribe our channel and advertise the channel to make more people enjoy free advanced physics education. Thank you. Let's begin. Okay. Let's begin with our discussion with what is physics. So physics pursues formulating the underlying theory of matter, constructing nature, and moving around space. So we study matter, and matter is filling the space. The nature is composed of a space and that contains matter. And matters are not frozen, they are moving around. You'd like to know how they move, why they move, such like that. If we know the rule, then we can find a situation to make the matter move around what we want. That's the first motivation of studying physics. The empty space-time structure provides the elementary parametric space, so we begin with the space and time. But in empty space, there is no difference in time. So there should be something in space. And if something doesn't move at all, then we do not need this time at all. So something should move. And we would like to construct a theory to find the rule of that motion. For example, equation of motion constructed by the Newton's law of motion, something like that. Elementary building blocks constructing the matter and their fundamental interactions are of major interest in physics. So, what kind of force or power that makes something move? Okay, you'd like to find out the building block. The matter can be divided into small pieces. For example, you know a molecule, and molecule can be divided into atom and electrons surrounding them. An atom is composed of a nucleus, and nucleus is composed of protons and neutrons. So we'd like to know how they bind, how they bind to make a bound system. For example, in the nucleus, there are so many protons and so many neutrons. Neutrons are electrically neutral, so there should be no attractive force among them as far as the electromagnetism is concerned. And there are so many protons, they are positively charged. So according to Coulomb's law of force, any positive charges repel each other. So how do we understand? How do we understand why so many protons are trapped inside a tiny space, even though there is a very strong electromagnetic force? But actually there is another fundamental force that wins the game. So we'd like to find the building blocks of matter and study the fundamental interaction among them. That is the major interest of physics. Number 4, it assumes the existence of fundamental rules that are invariant. Okay, if there is a rule, it should be repeated. If it is not repeated at all, we don't have to understand the rule because it is not a rule at all. Nobody knows why such a rule is repeatedly uh, regulated, and any matter strictly follows the fundamental rules of nature. But that's fact. If it is not the fact, we must not learn physics because it doesn't repeat at all. The reason why we study physics is the rule is always abided by the matter. Number 6, mathematics is an important logical tool as well as a language with which rigorous analysis of physical phenomena are carried out. Okay, and many students are not able to distinguish physics from mathematics because they have studied mathematics for more than 10 years all along without thinking about actual physical problem at all. Unfortunately, more than 99% what you have learned about mathematics is genuinely the physics problem. That is that mathematical tools were developed to solve the physics problem, but nobody knows, nobody admit that, and even many people do not think. Many of the physicists who are identified as they are now identified as a mathematician. For example, Leibniz is a physicist, but they do not think physicist at all. Very strange because they are familiar with the formulas that were developed by Leibniz, but actually that was developed by physicists to solve the physics problem. So mathematics, physics has in many senses look very similar, but mathematics and physics are absolutely different one. And physics is based on the real fact. Mathematics is based on imagination. And mathematics is perfect and physics is not perfect at all. Nature is perfect. However, what we want to do with physics is to find the shape of nature, or to find the rule of the nature. But mathematics, it is definite, it is never wrong because mathematics has nothing to do with the real world. We must admit that point, then it is a very good starting point to study physics. You will find at some point our problem solving procedure looks very mathematical, but at the very end or in the middle of our problem solving, we many times abandon mathematics because that mathematical assumption that we have made at the starting point is proved to be at some point against the experiment, for example. A very famous example of this is Michelson-Morley experiment. Michelson developed a very accurate machine, very accurate device to measure the speed of light. He wanted to find the relative velocity of the Earth with respect to the ether. Ether was believed to be the medium of the electromagnetic field. However, at the end of the day, he was not able to measure the relative velocity between the medium and the Earth. That means the speed of light is always the same in any direction, even in Earth or space. In his derivation, he began with the assumption that Galilean transformation works and space is Euclidean. But those assumptions, basic assumptions, were proved to be wrong. For example, at such a point where all of your assumption is proved to be wrong, then you have to abandon mathematics. That mathematics means our basic assumption of mathematical model. So we could modify mathematical model because a mathematical model is a model that can always be changed, but we can never be able to replace the nature. That's the difference. Okay. That such kind of event, once such kind of event appears, the history changes. The basic assumption that everybody believes it to be true is replaced with something else. The history changes. That was made by Einstein, that space-time is not a Euclidean space, but a Minkowski space. So another mathematical model appears. Someday, one may replace that mathematical model to explain the nature, then the history will change again. Number 7, any mathematical imagination that cannot be experimentally accessed or confirmed is not physics. Understood? Why do we study physics? The primitive intellectual curiosity of a human being to understand the universe is the most fundamental reason for studying physics. So every elementary school students have such kind of curiosity. Everyone in this class had those curiosity too when they were young, when they were a child. But many people who are still curious about the nature's hidden structure, then they change physics, they change history. Number 2, physics is the fundamental science of which any other branch of science is standing on. Sure, any science, any engineering. Physics provides the guiding principle of every branch of engineering. If you do not know the physics at all, then you cannot build a stable structure. For anyone who wants to look for a better understanding of science of engineering beyond the well-established field, beyond means you you have run out of any information that are known for many people. But if you approach an extreme state, then you have to do it yourself. Test your theory with the real experiment. Then problem solving technique is quite necessary to solve those problems. Then your general physics, your training in general physics may help you with solve such kind of problem. Physics does not tell you simple formulas that can be copied and pasted. Physics is for the people who wants to develop some new idea. What we study in this course? This course consists of the 28 lectures. And we focused on this semester called X series. We first focused on Newtonian mechanics. In the next semester called Y series, we study electromagnetism. And heat and wave, especially the electromagnetic wave that propagates in space. In anything discussed, almost 99% of matter what we study, except for photon, does not travel very fast. Very fast means the speed of light. The speed of light is the maximum speed any natural object can move. And if it is the case, if it is very slow and the size of matter is reasonably large, reasonably large means it is much bigger than the size of molecule or atoms, then 99% Newtonian mechanics works. However, if the particle becomes very small to approach atomic size or less, then Newtonian mechanics breaks down. If something moves very fast with the speed of light, then Newtonian mechanics breaks down. We need Einstein's relativity. So, in the Y series, we study electromagnetism, relativity, and based on that, the propagation of electromagnetic fields and heat transfer, the thermodynamic theories. We will end up with entropy study in this section, in this first semester. So any law of physics that governs the motion of particle must be invariant in any inertial reference frame. The frame of reference was first introduced by Galileo, and later Newton's three laws of motion was developed, and that is the fundamental background of Newtonian mechanics. To describe the motion of matter in Newtonian mechanics, we assume the space is a three-dimensional Euclidean space. Three-dimensional Euclidean space includes one dimension, two dimensions, and three dimensions. In principle, mathematical extension to n-dimensional Euclidean space is possible, but mostly we will consider focused on the three-dimensional space. Euclidean space is typically understood as the space in which the Pythagoras theorem works. That is a very simple explanation for Euclidean space. And there is another assumption: the space is isotropic. Isotropic is all of the three dimensions are independent, and there is no preference of the choosing three directions in three-dimensional space. If you are living on Earth, then you are very difficult to admit the fact that space is isotropic. For example, sky and ground, they are not isotropic at all. But if you erase everything in the space becomes isotropic. It is a very abstract idea because it is almost impossible for us to think about the space erasing everything else surrounding us. And each space, as well as time, they are homogeneous. The 1 centimeter in here and 1 centimeter in New York, they are the same, something like that. Such kind of isotropy and homogeneousness you are acquainted with such kind of situation when you learn mathematics. But when you learn physics, you must not take them for granted. This is not mathematics class. Mathematics, if they say that they are uniform, that's it. However, in physics, it is not always natural. You must always ask question why such kind of assumption is correct. So the people who have such kind of fundamental question can change the world. In comparison with mathematics, even though we used almost the same notation as mathematicians use, variable x in mathematics usually stands for a real number that does not have any dimensions. It's just a number at all. In physics, 1 does mean many, many things. 1 can mean 1 hour, 1 meter, 1 kilogram. For example, can you add 1 meter to 1 kilogram? It is stupid to add those numbers. 1 and 1 can be added to make 2. However, 1 meter and 1 kilogram cannot be added. So, any number in physics has its own dimensions. Sure, sometimes it does not have dimensions. That is called the dimensionless. So, physics has the same variable x, but that x is not the same as what you learn in mathematics. Without physical dimensions, there is no meaning of the number at all. During our course, we use various mathematical tools. So, vector calculus and usual calculus and analytic geometry and whatever. Differential equation, partial differential equation, differential geometry. That does not mean you have to take the mathematics course in advance. Any mathematical tools, what we need, will be developed by ourselves. And you I hope you do not take an additional mathematical course to follow this class. If you want, you could, but it only spend your time. If you do not want to, if your main goal is not to be a mathematician, do not take additional mathematics course in order to take this course. I say repeatedly. And the reason why I'm telling you like that is many students do not study physics at all, and they misunderstand that the reason why they do not understand the physics problem is due to the poor understanding of mathematics. No, that's not at all. Any mathematical tools we require to solve some problem, we develop by ourselves. Just follow this class. Every mathematical tools are developed in a self-contained form in this class. Okay? Actually, almost all mathematical objects you have learned has their own physical realization because they are all almost all originate from physics problem. For example, a vector. The prototype of a vector is a displacement. And its first order time derivative is velocity, and second order time derivative acceleration, and multiplied by the acceleration multiplied by mass is a force, that they are all vectors. Those physical quantities are expressed in terms of vectors, and vectors are compactly expressed in terms of Cartesian coordinate system. That is called analytic geometry. Euclidean geometry does not use any coordinate system, but Descartes introduced the coordinate system using basis vectors. And Cartesian coordinates are three linearly independent vectors. They are orthogonal, and for convenience, their lengths, all of the basis vectors are chosen to be 1. In Cartesian coordinate system, it is natural to introduce a matrix algebra to compute the component relations. For example, the basic operation scalar product that determines the angle cosine of the angle between two vectors is called the scalar product. And that scalar product can be expressed as a sum of products of components, Cartesian components. It is natural to introduce the product of two matrices. One is a row vector and the other is a column vector. So when you learn mathematics, you must be confused with the various operations and the various mathematical objects. But because of physics, when we write something as a mathematical word, that we have a real entity that is to be expressed. So it is much easier for you to understand what you are working on because a real object exists in physics aside. The scalar product and cross product that determines the angle between the sine of the angle of the two vectors. For example, magnitude of the cross product of the two vectors is the area of the parallelogram that is spanned by the two vectors. And cross product itself is a vector that is perpendicular to the plane. where the two vectors multiplied, that are multiplied, are placed. So it is very easy to understand the mechanism of rotation using cross product. So anyway, the matrix algebra is intrinsically implemented in the calculation of various vector calculations. In addition, equation of motion of Newton's three laws of motion is composed of a set of linear differential equations. So it is natural that you have to solve a set of system of linear equations. So to solve the linear equations, you have to find a way to find the inverse matrix to find the solution. To find the inverse matrix, you have to be able to find the determinant, and the determinant is closely related to cross product. To find the inverse, you have to find the determinant. All of the tools will be developed during this course. We will spend a lot of time to find the equation, of motion and to solve the equation of motion based on Newtonian mechanics. That intrinsically, equation of motion has a double derivative. If you have an equation with a single derivative, that is a problem of integration. Just a single integration will give you the answer. If you have double derivative, sometimes if double derivative is a simple function, you can integrate twice. However, if it is not the case, for example, double derivative and single derivative and function itself, they are summed together. To find out the solution, it is a rather different from what you have done with the previous case. But we will find how to find the solution coming from physics problem regarding the equation of motion that contains the double derivatives that are called second order linear differential equation. As far as a wave is concerned, it is extended to the partial differential equation because we have to consider the spatial derivative as well as a time derivative. Later part of this lecture contains thermal physics that contains many body systems, and in the middle we have a system of particles to consider rigid body or rigid body motion or wave. So in many sense, it looks very similar to mathematics, but as I have told you repeatedly, physics is not mathematics. Okay, this is the real start of a physics class. Postulates of space, time, and mass. The physics began with Galileo, and science began with Galileo. So physics is the father of any science in that sense. Why? The law of nature was the first studied law of nature. The nature has some rule that repeats. That's the main idea. And the law should be described by an observer. An observer has a relative velocity. So different observer may have different observables, even though explicit values components, they may be different depending on the frame of reference who is observing the event. One can find the relationship, one can find the translation between the two observers. So the introduction of observer. So observer means somebody who is watching the measuring the experimental fact. That is a reference frame was first introduced by Galileo. The postulates of Galileo is the time is flowing with the uniform rate. The 1 second today and 1 second tomorrow, they are the same. This is basic assumption. If it is not the case, we cannot compare any two measurements. And there, these are assumptions. In physics, we say a big assumption that covers, that is related to so many things, a fundamental assumption that is called a postulate. So space is assumed to be uniform, that is homogeneous along any direction, x-axis, y-axis, z-axis. And there is no difference at all between the x-axis and y-axis. For example, we could have chosen the y-axis to be x-axis and z-axis to be y-axis, something like that. For example, we could have chosen north as the north currently we are using, but we can replace the south and north. The physics doesn't change at all. In many cases, we study point-like particle, but in fact, there is no point-like particle at all. This is just a simple approximation. Remember, point-like particle does not exist at all, but this is a good approximation in some sense. Because I have repeated so many times, you can read it through by yourself about physics is not mathematics. Again, mathematics does help, but it's not a terminator, but that means that it does not give real answer. It may give an intermediate answer. But at the final stage, you have to interpret. If you made use of some mathematical formula, that you have to find if that mathematical answer is really physical or not, because nature is not a mathematical model. Let us consider the physical dimensions. As I told you, in mathematics, x, y, z, they are just numbers without any physical units. However, if I write down, for example, this is a three-dimensional vector, and these are coordinates. X coordinate is x1, y coordinate is y2, and z coordinate is x3. So we can make use of Cartesian basis vectors to write down the three-dimensional vector. All right, x1, x2, x3 are all real numbers. Okay. However, in physics, even though I do not write down the actual physical dimensions at all, it is assumed that x has its own dimensions, physical dimensions. For example, this is a displacement or position vector then x has the physical dimensions of length. It is not a pure number. It is a pure number multiplied by a unit. That unit has the physical dimensions of length. That's quite important. So if you write down the variable, first you have to write it in italic form. Some number has the italic form that is called the physical variable, and that number has its own number, dimensionless number in it. In addition, it contains its own physical unit. Okay, the unit is a unique name we assign to measures of a physical quantity. For example, we use International Standard Unit, so that is called SI unit. In the standard unit of length is 1 meter. We are familiar with this, but you have to know this M is Roman. It is standing up. It is not slanted. So unit should be written in a Roman type. Very important. And the unit is a case sensitive. For example, meter should be written in a lowercase. It should not be written as capital M. And actually capital M is not a meter, it is a mega. All right, it is a million. 10 to the 6. This is number. Even though it is Roman, 2, however, it is a capital letter. Capital letter M is not the unit meter. All right. Among the units, there are base units. Base is a basic. It's the fundamental units. 3 fundamental units are called mass, time, and length. These 3 units are called the base standards. Base. However, it is convenient to use, for example, more complicated objects. If you have so many powers in mass, length, and time, it is very difficult to distinguish. So we need some derived units. Derived units is a practical unit that is not fundamental, that can always express it in terms of the 3 base standards, mass, length, and time. But in practice, for example, watt. Watt is a watt. We use a capital W, named after James Watt. So power is a physical variable, and power is work per unit time, and work is force times displacement, and time. Force is mass times acceleration, and acceleration is the distance divided by time square. If we consider everything all together, mass, replace mass with m, and replace the displacement, the length dimension as L, and time in this form, we end up with this kind of form. So you have many chances to write down a derived unit in terms of base units in powers m, L, and T. with certain powers. Okay. Among various units, nature provides us constant units. For a long, long time, we were not able to find whether this is a really natural constant or not. But indeed, we have found at least these three quantities are naturally determined, and it is of no use to determine it more accurately. For example, we first fixed the dimension of meter. We kept the prototype of meter, but actually it is a matter. It depends on the length of 1 meter. The prototype changes depending on temperature. It is very stupid to express the speed of light in terms of such a very inaccurate object. So we have agreed that fix all of the fundamental constants as exact number and redefine those absurd quantities like meter, something like that. That depends on the fundamental quantities. So as of 2019, it is absolutely fixed to be speed of light is 299,792,458 meter per second. Okay, this is exact number. If you want to write down more numerical number, if you wish, it should be 0, 0, 0, 0, 0 to infinity. So these does not say the significant figures. Significant figures representing the speed of light is 299,792,458 and 0, 0, 0 to the infinity. Okay, so it is exact. This is an exact number. Another fundamental constant is called the Planck constant. Planck constant determines the energy of a single photon, has the frequency nu, and the slope, the ratio of energy and frequency nu is the Planck constant. And this one is also an exact number. Exact number. There is no uncertainty at all. Another absolute value is the electric charge of an electron. And actually, the electric charge of an electron, charge Q of an electron, is minus E. So this is negative value. So absolute value of the electric charge of the electron is 1.602176634 and 0, 0, 0, 0, 0 to the infinity times 10 to the minus 19 Coulomb. So this is a kind of new definition of Coulomb. The inverse of this, reciprocal of this number, is the Coulomb in units of electric charge, electron's electric charge. There are a few more exact SI units that includes 1 second. 1 second is based on the cesium-133 atom ground hyperfine levels of ground states repeats. It has on periods so many times. So using this period, we determine 1 second as an inverse. And 1 meter is now, because the 1 second and speed of lights are determined accurately, exactly. So 1 meter is indirectly defined by the distance of travel by light in vacuum in the inverse, the reciprocal of the 458, 1 this amount of second, a very tiny second. Again, kilogram is determined by this Planck constant. And actually, Planck constant is related to the energy, and kilogram is for the mass, and actually the rest mass of a particle is determined by E equals mc squared. Rest mass times the speed of light squared has the energy. So in such a way, one can determine 1 kilogram indirectly. Because 1 second is exactly defined and electric charge is exactly defined, the current, unit of current called ampere, is indirectly defined now. Another exact number is a Boltzmann constant that determines the mechanism of a gas. So gas constant is actually the Boltzmann constant, gas constant called R, capital R, usually used in chemistry, is a Boltzmann constant multiplied by Avogadro's number. And these two numbers are exactly defined now. There is no error at all. These are all exact numbers. You can follow some examples. Solve the examples if you can follow this. If you do some numerical calculation involving units, some units has, for example, time unit has second, minute, hour, day, year. There are many units depending on our convenience. So if you want to translate some unit to another, it is usually useful to multiply 1. And one can, for example, a over a equals 1. So you choose 1, you must write down 1 to include. 1 is to include something you want to erase in the denominator. For example, 1 equals 24 hours divided by 1 day. You want to replace day with the hour. Then you must multiply 1 that has the denominator that contains day in the denominator. So write down 1, day. And you want to replace this 1 with hour. Write down hour. Are they the same? No. 24 hours is 1 day. Okay, so what you want to do is just multiply 1 in here, and day cancels to find out 24 hours. And then you want to replace hour with minutes, then you again multiply 1. That 1 is to include hour in the denominator. What you want to do is to replace this 1 with minute. 1 hour is 60 minutes. So 60 minutes divided by 1 hour is to be multiplied in here to cancel hour, and you find out the minute. In a similar manner, 60 seconds per minute is multiplied. So you cancel minutes to find out 24, 60 times 60 seconds. So the answer is this. This is called the chain link conversion. Chain link conversion is called the multiplying one. And there are so many ones, but what you want to do is to cancel. Your objective is to cancel the original unit and replace this one with another unit. And if you know the equivalence between 1 day and 24 hours, just multiply this. You can follow the scientific notation. In scientific notation, write down in this way, there is a parenthesis and multiplied by 10 to the something. So these numbers represents the significant figure. These are significant figure. However, this figure has its own uncertainty coming from the measurement. The uncertainty is contained in the what's that? This parenthesis. And what are these two digits? This one means that this last two digits has the uncertainty of this amount. So sometimes we can write 1093836 plus minus 0.0000000 and 11. This is too long, so many times we use a parenthesis to express that last two digits. Last two digits has an uncertainty of 11. All right. This is a notation for scientific notation for the numerical value. When writing down numbers, we have so many powers, 10 to the something. So we have some abbreviation called prefix. You should be familiar with the centimeter. Okay, what's centi? 10 to the minus 2. Millimeter, micrometer, nanometer, picometer, femtometer, atto, zepto, yocto. You must memorize all these SI prefixes. These are all less than 1, and these are all greater than 1. Deca, hecto, hectopascal. When you measure the pressure of typhoon, size of the typhoon, the strength of the typhoon, you use a hectopascal. Kilo, kilogram, mega, megahertz, gigabyte. Now they use a terabyte or petabyte hard disk. Exa, zeta, iota. All those numbers should be memorized. These pairs are reciprocal. So if they multiply, then it will produce the unity. The later part of every lecture, I'll contain the self-test. And self-test will remind you what you have learned and sometimes what you have never learned before. But you can search for internet, but it is very easy to find this answer. And sometimes I will write down all the details of derivation, but sometimes for your imagination, I won't provide the answer until the end of. I will never tell you the real answer to this open question. But it was a very good, it is useful for you to review what you have learned in this class. Okay, that's it for today's lecture, and please go ahead with solving self-test for 15 minutes. Thank you.